Okay, so this is the last video in the P6 series, radioactive materials, and this one is about how dangerous radioactive materials actually are. So is it actually a risk to be near them, and if it is, how risky is it? Now, the reason that radioactive materials are a risk, because they are, is because they are ionizing, okay? Now, ionizing radiation is just radiation that knocks out an electron from a atom. So ionizing radiation knocks out electrons from atoms. Now it does this, sorry, I just finished writing that. It does this either as its particle, if it's an alpha or beta particle, or as a wave by hitting the electron. So if I think about here, if I've got an alpha particle, which is quite big, remember an alpha particle may be about this size compared to my electron here. If that's travelling along here, that's going to collide with that electron and knock it out. Okay, so then that atom will have one less electron, and we know that an ion is an atom with a different number of protons to electrons, so electrons missing or added, and that means it's got a charge. So a positive ion is one that's got less electrons than protons, it's got a positive charge overall, and a negative ion is one that's got more electrons than protons, so it's negative overall. Now, if we're knocking an electron off, we're going to turn this into a positive ion. It's going to have more protons than it does electrons, and that means that it's going to be more likely to partake in chemical reactions, okay? So an ionized atom is more likely to take part in chemical reactions because they want to have this gap filled. It leaves a gap, and that gap they want to be filled. So if there's an electron hanging around, it's going to jump to this space, and that might be from a different element maybe, and then we get a chemical reaction. Okay, so an alpha particle would do that. Now, a beta particle is a lot smaller. A beta particle is about the size, well it's a high-speed electron, so it's about the size of a high-speed electron, so it's about this big. So you can see already that if that particle hits here, then it probably will knock this one out. However, if this particle is here, then it's going to go through my atom, and it's going to go through without hitting, okay? So alpha particles, let me write beta next to that, alpha particles, because they're bigger, are much more ionizing. Okay, so alpha are the most ionizing, and that's just because they're bigger, so they're more likely to hit something. Now finally, we've got our gamma radiation, which is just a wave. Now I can't draw the size of a gamma radiation because it's too small. I'm going to do it up here, okay? And it's a tiny little squiggle. Now it's much, much smaller than an electron, but I can't draw much smaller because that's how big my pen is. So a gamma radiation is even less likely than a beta particle to get through and not hit an electron. So it's the least ionizing. However, it's often seen as the most dangerous because it's the most penetrating, and that's because it's the opposite of this. So an alpha particle is the least penetrating because as soon as it gets through paper, because it's so big, or anything that's in the way, so paper, your hand, even the air, because it's so big, it's more likely to hit something on the way and stop being an alpha particle, because as soon as it gets 2 electrons, it becomes helium. Because remember, an alpha particle is just a helium nucleus. So all it needs is 2 electrons to become a helium atom. And then it's a stable, it's a noble gas, so it's a stable atom that doesn't want to change anymore. A beta particle, because it's smaller, has got less chance of hitting an electron even in an atom, and therefore it's more penetrating, it can go further without interacting. A gamma particle, because it's the smallest thing, is the most penetrating. So if you're near an alpha source, as long as you're more than like a metre away, you're pretty safe. A gamma source, you can be hundreds of kilometres away and it can still probably get to you because the chances of it hitting an electron on its way to you is tiny because it's so much smaller than the space in an atom. Okay, so gamma radiation is the least ionizing and therefore it's the most penetrating, whereas alpha radiation is the most ionizing and so it's the least penetrating. You won't be able to read that at all, but you know, you get the idea. Right, so ionizing radiation is that it knocks an electron out of an atom. And why that's an issue is for humans because of this kind of rough diagram here. So this here is meant to be my radiation. This is a gamma ray, basically, because it's a wave. Now, if that gamma ray gets into a cell, or any of this one, to be honest, any of these radiations, if they contact an atom in a cell, especially if they get into contact with an atom in the DNA, and they knock an electron out of that DNA, they have damaged the DNA. So it damages DNA. Ionizing radiation damages DNA. Now, from biology, I am not in any way a biologist, so it's probably better to use your own knowledge or ask a biology teacher about this, but as far as I know, when a cell replicates, remember it completely replicates its DNA exactly as it was. Now, a cancer cell is just something with faulty DNA, or it's a mutated cell that then multiplies quite quickly normally, and it becomes a tumour. So the DNA becomes faulty, and then when that cell multiplies, it's mutated, and it can become a cancerous cell. Okay, and then that cancer cell grows and grows, it replicates and replicates and replicates, and becomes a tumour, not a tumour. So ionizing radiation is dangerous because it damages DNA, which then, when the cells replicate, can cause the growth of a cancerous tumour. So when they say radiation causes cancer, it can lead to cancer, yes. It's not always going to happen, but it is one thing that can happen. Okay, so that's why radioactive materials are dangerous to humans. But how dangerous they are depends on the dose, and we're going to talk about that in a minute. So there's 3 key terms we need to know about, and they're in this next slide here. Okay, now there's something called background radiation. Now background radiation is low level, so there's not much of it. It's everywhere, you cannot escape it. Okay, it's background radiation everywhere, happens all the time. And it's just from the natural radioactive sources in the Earth. So it's from natural sources. So background radiation is radiation that's always there. So we're never free from it. But there's not much of it. It's really low level. Now, when I say natural sources, they might ask in the exam what these natural sources are. And they are usually rocks. Rocks have got lots of radioactive material in them. And also cosmic rays from space. Okay, so we get lots of cosmic rays from space. And we get them from rocks as well. So these are our natural sources. So background radiation is there all the time. You can't get rid of it. Obviously, it can't harm us that badly because we've all lived with it for thousands of millions of years. It's always there, and you're always exposed to it. Okay? Now, irradiation and contamination are 2 different things. They don't mean the same. They're kind of in a separate league to background radiation, but I thought we'd get all the definitions in at the same time. So, irradiation happens if you are near a radioactive source. So I should put at the top there. So if you are near a radioactive source, you are irradiated by it. So if you've done in your lessons, if you've done the practical with the Geiger counter and the different radioactive sources, you've been irradiated because you've been near that source. It's not too dangerous generally, especially the ones in class anyway, because we wouldn't have that really dangerous stuff out. But the nearer you are, the more likely you are to be irradiated. So it's just being near a radioactive source. So once again, if you stand near a power station, or if you work in a power station, you're going to have some irradiation from around you. Contamination is a bit more dangerous. Contamination is if a radioactive source is on you or in you. Okay, so it's a bit more severe than irradiation. Irradiation is being near. Contamination is actually it being on or in you. Now, on is when it's going to be on your skin or clothes. So if you've touched it, that's touching. And then in is, well, it's inside you. So it's if you've breathed it in or if you've eaten it. So breathing or eating it. So if you've eaten contaminated a radioactive source, you are contaminated. If you've breathed it in, you're contaminated. If you've touched it, you're contaminated. So that's why we're going to have a stage method later on, but your teacher, when they were using the radioactive sources, they were able to use tongs so they didn't contaminate themselves. You were all irradiated, but hopefully none of you were contaminated. That's a big difference to know. Irradiation is being near, contamination is it being on or in you. So it's kind of worse. Right, so knowing that, we need to know about how dangerous they actually are. And how dangerous radioactive materials are is all to do with radiation dose. So how at risk you are is all to do with this thing called radiation dose. And that, as you can see here, measures the possible harm that radiation could do to a body. So the higher radiation dose of a radioactive material, the more likely it is that that's going to harm you. So the stuff that's in school, the alpha radiation that is in school, which has a really low radiation dose compared to, say, spent fuel rods that are high-level radioactive waste that are kept underwater for 10 years in a nuclear power station, because they have a lot more risks. They've got a much higher radiation dose. So the higher it is, the more possible harm that could happen to your body. So radiation dose is measured in something called millisieverts. I can never say it very well. measured in, it's spelled like this, M-I-L-L-I-E, no, M-I-L-L-I-S-I-E-V-R-T-S, and its symbol is MSV. Okay, so radiation doses are measured in millisieverts. It depends on two things, okay? It depends on two things. One, the amount of radiation that you've been exposed to. So if you were near a small piece of radioactive material or a huge piece, obviously the huge piece would be more dangerous because it's more likely that some radiation has got to you. So amount of radioactive material. I apparently can't write and talk at the same time. And also the type of radioactive material. Now, which type it is depends where you are. So the type here, if the source is outside your body, then gamma is the worst. So outside of your body, gamma is the worst, and that's because, as we said before, it's penetrating. So it can get through your skin, it can get through your muscles, it can get through into your body. And then it can ionize an atom, and that can cause problems and tumours and that kind of thing. So outside your body, gamma is the worst. However, inside your body, so if you've eaten it or breathed it in inside your body, alpha is the worst. And that's because of the complete opposite. It's the least penetrating. So if you have gamma inside of you, most likely it's just going to come straight out and not bother you. If you've got an alpha particle inside of your body, it's probably not going to make it out. It's probably going to ionize, 99.9% going to ionize an atom within your body, and that's what can cause the problems. So inside the body, alpha is the worst, outside gamma is the worst because of their penetration and ionization kind of properties. So you could have lots and lots of a not too harmful type, or a little bit of a really harmful type, and it's kind of a balancing act between the two. So the normal background radiation, I'll put this up here, in a year, background radiation we get from just everything around us is about 2.5 millisieverts. Okay, so we always get some. A nuclear power worker in their job would probably get about 0.18 millisieverts extra on top, so actually not that much because they're really protected. We'll talk about why that is in a second. So it's always going to happen, we're always going to get some, but how much you get depends on the amount of radiation you're near and the type. So if you're in a nuclear disaster, then obviously it's going to go up a lot more than 2.5 millisieverts. Okay, so we've just talked about all the harm, that all the risks that we have associated with radioactive materials. We haven't really thought about any uses because they are actually really useful. There's a lot of things they can do that nothing else can, and they can be really, we use them for good things. Now the first thing, and probably one of the most famous things that can be used for, is radiotherapy. Okay, radiotherapy is it's the physics version of chemotherapy. It uses gamma radiation, and basically it's a way to kill cancer cells. Now it works because of exactly as we said, ionizing radiation, or gamma radiation. If it hits your, if it penetrates into your body, it's got a chance of ionizing a cell, and that can cause it to mutate, and usually it dies. So if you've got a cancerous tumour, then if you have a source of gamma rays directed directly over that source, that tumour, then those gamma rays are probably going to ionise some of those cells and kill it off. Now, obviously with radiotherapy you have to be really careful, because if you directed that gamma source over a different part of the body that didn't have any cancerous cells, it doesn't care what type of cell it's hitting, it will kill it. So if you can direct it over the tumour, then that's great, it can kill the tumour. If, however, you can't, it's a bit difficult, because then you're going to kill healthy cells, or you can lead to more cancer. But if you've got cancer, then the risk of getting another cancer is much, much smaller than the chance of the radiotherapy curing you. So that's why they use it. You wouldn't get it for fun. You only use it if you actually got cancer. Gamma rays are also used to sterilise things. So they can sterilise two types of things. So that's the part wrong. Sterilise. Now, they sterilise surgical instruments. So if you go into surgery, it's been sterilised with gamma rays. And also some types of food. Now, actually in the UK, it's spices and herbs. Nothing else is allowed to be. And you have to be told that's the case. But they can sterilise things, and that is because of the same thing. It kills cells, okay? So this cancer bit, it doesn't just kill cancer cells, it kills all cells. So if you put your surgical instruments into a steel plastic bag with like no air, etc., airtight, and then you pass it under a gamma radiation source. That gamma source will kill any bacterial cells on those surgical instruments. When you take them out your bag again, they're fine. They've been irradiated. They've not been contaminated. Okay, so you need to write that down. I'm going to write not contaminated. They're just irradiated. So we're okay. We're safe. We're not going to have any issues once they're used during an operation. Food's the same thing. So spices and herbs are in their pot. They get put under a gamma source, and it's irradiated because the actual gamma source doesn't come in, the gamma rays don't come into contact, or the gamma source, I should say, doesn't come into contact with the spices and herbs. It's just nearby. So it kills any bacterial cells, basically. So sterilisation is killing any bacteria or other virus germs. It's also, in another medical way, gamma radiation and also beta at times are used for medical tracers. So you might have known someone who's had a kind of a test with medical tracers where you swallow some radioactive material, something like barium maybe, and then they have something called a gamma camera which they hold over you, and it produces an image of where the radiation is. So you have to kind of target it and use special ones, but there's one example where I think it's tactinium, I can never say it, tactinium, and that can be used to see about kidney function, because if your kidneys are functioning properly, then all the tactinium should pool in your kidneys, and if you hold a gamma camera over there, the camera will pick up the radiation from there. If you have black spots where your kidneys are, that's showing that it's not moved to where it's meant to go. So you've seen that your body isn't working properly. So a medical tracer is also a good use. One more thing for gamma rays is that it's used to search for cracks in kind of industry. So if you're kind of welding or with metals and stuff, gamma rays can be used to search for cracks in welding and other industries. That's another gamma one. There's two more that I'm going to talk about really quickly that use alpha radiation. The first is smoke alarms. Okay, so your smoke alarm, which I hope you all have, it uses alpha radiation, not gamma, alpha. It uses alpha radiation to work because basically it has an alpha source and a detector. So there's my detector here, and there's my alpha source. So the alpha source is streaming towards it. Now, if there's a fire and you have smoke, that's why it's called a smoke alarm, not a fire alarm, the smoke's going to get in the way here and get in here. And the smoke is going to mean that these alpha particles can no longer get through. So as soon as that detector detects that there's no alpha particles coming through, it knows that there's something in the way, and usually that is going to be smoke. So that's how smoke, and then the alarm will go off. If the detector can't detect alpha particles, the alarm goes off. So that's how smoke detectors work. They use gamma rays. And the final one is a similar kind of thing, is testing the thickness of paper in paper factories. That uses alpha particles in the same way. So, thickness of paper. So instead of smoke there, you have a thin piece of paper and you get a certain amount of alpha particles getting through. If you thicken that piece of paper, then they're not going to get through anymore because they'll be ionised. But they're kind of two ones you don't need to know about as much. These are the main ones: radiotherapy, sterilisation and medical tracers. Okay, so they're the uses of radiation. There's lots more, but they're the main ones that you should need to know about. So, if it's a useful thing, obviously some people have to work with it, but they have to protect themselves as well, because we know that they can be dangerous. So they might have some uses, but the risks, there's benefits, but there's also risks there as well. So there's lots of different ways that nuclear workers, that's what you call someone who works with nuclear radiation, protect themselves from radiation. Some of them are really obvious, okay? They're going to wear protective clothing. So you might have had a scan in hospital, and they usually wear things like aprons and gloves, masks, things like that, just kind of clothing that's going to stop that radiation getting towards them. So kind of usually overalls. Or if you've ever seen a crime drama or something where they think they've got a radioactive problem, you see the SWAT team go in, they have, not really a SWAT team, usually scientists, but they have those full body kind of morph-esque suits on. They also wear special devices, usually badges, to measure how much radiation they've been in contact with, monitor the dose. So they'll have a badge that's got some film in it, and if that film goes cloudy, that means that they've been exposed to too much radiation, so they can see that and then they can act accordingly. Obviously, you're not going to want to be there for any longer than you need to be, so a minimal exposure time. So they're not going to stand around having a cup of tea near the radioactive source. They're going to make sure they do what they need to do near it as quickly as possible and then move away. So that's going to reduce the risk. if you have to touch it, you'll have seen this in your practicals at school with the radioactive sources, your teacher will have used tongs. So some places will use tongs, or if it's a factory, you might use a robotic arm to actually touch the sources. Because once again, then you're not being contaminated. This is all to reduce to stop contamination and reduce irradiation. And finally, a sensible one that we do in the lab for other chemicals: label clearly the containers, so you know what's dangerous and what isn't, and what you have to be careful for. So these are just kind of, there's how many steps there? 5 or 6 steps that helps the nuclear workers protect themselves. Okay, so they're going to reduce the contamination and the irradiation. So that is P6 basically done. That's all the main points. I think it's in about an hour and 20, so it's not too bad. Hopefully it's useful. Make sure you have a go at some passover questions, and if you need to look at something again, ask me in lessons, or watch these videos again. Thank you.